This is the UE1, my 1-bit homebrew vacuum tube computer that I've been building from the ground up for about 3 years now, and it just calculated Fibonacci up to 21 perfectly. Not only that, it just did it again with no fault whatsoever. That means that this UE1 is fully functional. It's doing logic operations, it's doing arithmetic operations, it's doing loads, it's doing stores, it's doing all sorts of computery things, but there is one thing that we haven't actually tried to do with it yet, and that is conditional branching. Before we get too far ahead of ourselves, when we left off in the previous episode, it was not calculating Fibonacci to 21 successfully every time. Now, a lot of you guys left comments saying it sounds like I'm not initializing something correctly, but actually the first like 23 instructions on the tape are specifically for initializing the CPU and clearing out memory. And the failure we were seeing is within the first 3 instructions. The first instruction is 1. It forces a 1 into the result register and a 0 into the carry register. Then we do IEN and OEN using the result register as a loop back, and all 3 of these instructions are executing perfectly. Where we're failing is on the next instruction. This is a NAND that NANDs the result register with itself. So whatever the result register is storing, it should be flipped. If it's storing a 1, it should become a 0. And this instruction was failing, which means that when we get to the next set of instructions, which are all store instructions, we're now instead storing a 1 into all of memory. So why is just the NAND instruction failing? And well, it's just, there's no two ways about it. You just got to get into it with a scope and follow traces around. So the other night I fired up Discord and hung out with a bunch of my buddies, and we just sat down and troubleshot this thing for about 4 hours. And we started at looking at the input into the result register. And as suspected, whenever we do a NAND instruction, that fails. So we followed back one step to the 4 input OR gate that feeds it, and one of those inputs looked nasty. So we followed that back to the logic unit, and again we're still seeing that same nasty voltage as we're propagating our way through the logic unit. We get through the backside of the logic unit, past inverter, and we're still seeing this same nastiness all the way up to this NAND gate. Now what this NAND gate is doing is it is acting as a sort of enable to allow data from the data bus to pass through into the logic unit. And so if this NAND gate is misbehaving, it's going to skew the way that that data passes through. And that's exactly what was happening. That vacuum tube was bad. That's actually this tube right up here. And once we had discerned that the inputs looked good, but the output looked bad, we swapped that tube and the whole thing sprang into life and started executing Fibonacci perfectly every time we hit the button. Well, not exactly perfectly. The last instruction on this tape is a halt instruction. That is working correctly, but the second to last instruction is supposed to ring this bell right here. And if I tell it to calculate here, it didn't ring the bell. What's worse is that sometimes the bell rings when it's not supposed to. Now I've taken this little driver circuit board over here off and tested it on the bench, and it's working perfectly. So the problem is between this driver circuit and whatever is feeding it from way over here. So I think it's time to pull the scope out and try to get this bell ringing like it's supposed to. Of course it didn't do it while filming earlier, but check it out now. I'm not sending it a ring bell command at all. It's just going insane all on its own. So I busted out the scope and did lots of probing. I was manually sending ring bell commands, checking the scope, and maybe it is my little bell driver board after all. I'm getting a weird oscillation backfeeding into my buffer that goes away when I disconnect the driver board. Check it out. Now we have a nice and clean signal with a clean ring pulse, exactly like it should be. Okay, let's connect it back up and see if we can see that oscillation on the anode. Whoa, That's gnarly looking. The occasional full low spike is when it spuriously rings, but I'm more concerned with that wicked low spike to 10 volts that then climbs back up and goes chaotic. Why is it that every time I don't want to build an oscillator, it oscillates anyways, and when I do want to build an oscillator, it'll never wibble wobble? Anyways, let's pull this thing off and see if I can bodge my way out of this mess. And don't worry, it took me hours and hours to figure out what needed doing. After much bodging and unbodging, check it out. It rings the bell perfectly. That's so exciting. It turned out it was a G2 or grid 2 problem. Normally when I'm building circuits with thyratrons, I tie G2 to the cathode and then I tie all of that to ground. And that seems to work really, really well. However, in this case, I'm actually tying the cathode to the relay coil, and then the relay coil goes to ground. But because I've tied G2 to the cathode, that means that G2 isn't going to ground. It's going to the relay coil. And this was creating an oscillation, and that oscillation was causing all manner of chaos. So what I've done is I've gone through and I've sliced up some of the traces on the bottom, and I now have the cathode going to the relay coil like it was before, but G2 on both thyratrons is going to ground via a 33k ohm resistor, and that has completely solved it. It rings the bell reliably every single time. The oscillations are completely gone. Every single instruction on this Fibonacci tape works perfectly. That Fibonacci program is using 11 of the 16 total instructions that we have in our instruction set, which is great. However, there's still two aspects of the machine that we haven't really used. One is external input. I have a bunch of toggle switches at the top that we can use to toggle in external input, and we haven't written any programs that makes use of those. The other is the input enable register and output enable register. If we use the output enable register in particular dynamically, we can do some really tricky stuff like conditional branches. So how does that work? Because that doesn't really make any sense. The program is running on a paper tape that can't go backwards. And since it's executed directly from the paper tape, we don't have any way to jump. But we're not building programs that jump, we're building programs that loop. So the 4-bit instruction is coming into the CPU, and depending on what instruction we're doing, we're combining the write signal being output from the CPU with a 4-bit memory address. If the memory address is between 0000 and 01111, we're either reading from the scratch register or writing to the scratch register. But as soon as the address hits 1000, if the write instruction is off, we are reading from the input switches or the result register in loopback. And if the write signal is on, we are writing to the output register. Now that write signal is the key here because it is controlled by the OEN register. So we can see that we have a store or a store complement instruction coming into an AND gate. And that AND gate is also receiving the value of the output enable register. However, if the output enable register is storing a 0, that means that the write signal can never go high. If that write signal never goes high, we never change any values in memory. And so what happens is after we turn that output enable register off, all the subsequent code runs, but it doesn't ever actually change any values in memory. So that section of code is effectively skipped. So let's take a look at a little program here that I wrote. We start with a 1 that forces a 1 into the result register, and then we do IEN and OEN using the result register and loopback. This is our standard basic CPU initialization. Now I've got a bunch of store commands following that. This is just to fill and empty the output register, so that way we can visually see that yeah, things are working like they're supposed to. Then after that, we hit a halt. And you can see I've got about 16 NOP O's after we hit the halt. And that's because the instructions are being executed directly from the tape. And when we halt, the tape still has a little bit of momentum to it, or rather the motor still has a little bit of momentum to it. And that causes the tape to kind of slide past the photodiodes for a little bit. So I kind of overkilled it with 16 NAPOs here. That should be plenty of space. So what's gonna happen is while it's halted, I'm gonna reach up and flip the toggle switches to input my first operand that I want to do an addition or subtraction with. After that, I hit go and it reads in the value of those toggle switches, stores it into the scratch register and into the output register. Then it halts again. And now while it's halted, I can also toggle in the next operand that I want to do an addition or subtraction on and send it on its way. Then we load in the value of the 7th toggle switch. I'm using this switch to indicate whether we're doing an addition or a subtraction. Now, if that value is 0, we're going to load a 0 into the result register, and then we're going to store the value of result register in OEN. If that value is 0, all of the following instructions will execute, but they won't affect memory in any way, meaning they're effectively skipped. So if the output enable register is ever on during one of these two blocks, it runs through and executes the following code. And if we look at this code here, this is a subtraction. We do a 1 to force a 1 into the result register and a 0 into the carry register. Then we add the result register with itself. 1 plus 1 equals 1, 0. This forces a 1 into the carry register. Then we load in the first operand from scratch register 0, and we subtract the operand on the toggle switch. Then we just do that over and over again for the next 6 bits. Then we get to the very end where it halts the paper tape, and we have now successfully added or subtracted 2 numbers that we toggled in via the toggle switches. And we can give that program a quick test by jumping into the UE1 emulator written in Quick Basic 4.5 here. If you want to play around with this emulator, I'll put a link in the description below to all the source code. Some people have already ported this to some pretty wild languages like COBOL as well as the G15. I saw that one just this morning, actually. I think we're going to have to dive into that one in more detail in a future episode. But for now, let's just go ahead and hit Shift F5 on this one. It's going to ask me where the file is located. It's in C:\UEASM. It's going to ask me what the file is called. It's called UE1 math, and we'll just go ahead and run at 100 Hertz here. It's going to fill the output register, empty the output register, and ring the bell. And now the processor is halted, which means the tape will have stopped, and it's waiting for me to toggle in the switches. So let's do a basic addition here, which means we're going to set the most significant bit to 1. And let's add 5 plus 3. So 5 is 1, 0, 1 in binary. We'll hit G to resume. It's going to take that 5, load it into the output register, ring the bell again to let me know it's time to input my second operand. And to do 5 plus 3, that's going to be 1, 1. So we'll put that in, hit G. It's going to do the addition. We should see the result in the output register, which is 1, 0, 0, 0. That is 8 in binary. 5 plus 3 equals 8. It just did some addition. Now let's do a quick subtraction. We'll hit G to resume here. This is going to loop. It's going to ring the bell asking me for my next operand. We want to do subtraction, so we're going to turn that most significant bit off. And let's do a 5 minus 3. So again, 101. We'll hit G to resume. It'll load that into the output register, ring the bell, turn that one off, turn that one on, hit G to resume. We should get 2 out of this. And yeah, there we go. 1, 0 in the output register. That's our binary for 2. So we just did addition and subtraction, which means that this program is good. All we got to do is turn it into binary, punch it out on the paper tape, load it up into the real deal hardware, and see what happens. To punch this out onto paper tape, we're just going to take the binary file here, which I've actually tripled up so that we can run the program 3 times without having to reload the tape. And we just need to send this to the 4070 paper tape punch over here via TerraTerm. So I'm going to come over here and I'm going to go File, Send to File, UE1 Math, do it as a binary, click Open, and there we go, punching out the program. Excellent. Oh man, look at that. It looks like it punched perfectly. We can see the long streams of knops that I had to slip in there for tape spin down whenever we hit a halt. Let's load this up and see if it works. To be clear, I'm not actually expecting it to work. I didn't put enough leader on it, so in order to get the tape to feed, it's like right on the bitter edge. So the first couple of instructions may not even work. Also, I hope I have enough knops in there for tape slowdown. We're gonna find out. I may be repunching this tape again shortly. Let's go ahead and just hit go though. It halted. So let's do an addition. We'll set U, U, and U. That's gonna be 5, 101. Let's hit go again. It did not load 101 into the output register. It loaded something else completely different. Let's do 3, hit go on it. And that should be 8. It is not. It is not 8. Okay. In order to troubleshoot this, I wrote a little debug program here, and all this program does is clear out the scratch register, clear out the output register, ring the bell, and then halt. Then while it's halted, I'll toggle a switch up here, and what it'll do after I tell it to go again is then copy the entire value of the switches up here into the output register using the same code that we use in our math routine. Then it'll halt, and that's it. That's all it does. So we'll run it, and something interesting happens here. So I'll hit go. Okay, it rang the bell. It's waiting for me to punch in a signal here, so I'll just flip this switch right here. We'll hit go again. And look at what happened on the output register. Instead of just copying the bit into bit 1 here, which is what it should have done, it also copied that value into bit 2. That should not have happened. And this happens for every single switch. So if I hit go here, cleared everything out, hit the bell, I'll flip this switch here, we'll hit go. And you can see we lit up 2 lights. It's copying each bit to 2 locations. There are 2 parts to understanding this kind of weird failure that we're having, and the first requires us to go back and look at the code. And whenever I do a load from the input register, I always load from a position that is 1 higher than the position that I store to. So load IR1, store to SR0 or OR0. The reason I'm doing this is because there's only 7 external inputs that I can read from. That 8th input is actually a loopback of the result register. The first toggle switch that we can read from the input register is at memory address 1001. So I'm loading from 1001 and storing to 1000. That's how we're getting this kind of double light thing showing up. Here's how the logic for the input is laid out. And along the bottom here, you can see we've got external switches and an external pin header. This pin header actually exists on the real machine, but that's not what we're using. We're using the toggle switches. Over here on the left, you can see that we've got all of our addressing set up. And this works beautifully well, except there's one thing missing from this collection of gates. There's no way to differentiate whether I'm doing a read or a write. So every time I'm doing a write, if one of those external switches is set, it blasts the value onto the bus. So I think that I can fix this by wiring in an extra input to all of these 3 input NOR gates that contains the write signal. So that's what happened. That's the failure here. And interestingly, it means that the scratch register was probably holding the correct answer to our math problem. We just had garbled output coming out because it's only the output register that's being affected here. The fault is on this big board right here, but in order to fix it, I'm going to have to connect a bodge to the board next to it. So I'll pull all the connectors off, remove the mounting screws, and then pull them off as a single unit. And this is not the first time I've bodged this board. I was having some signal integrity issues, so I added some extra pull downs, and while it cleared up the integrity issues, that actually is completely unrelated to the problem that we're diagnosing now. I'll bend up some new diodes and get them soldered into place. I'm going to need to connect 7 new diodes to the NOR gate input sections, all the while being careful not to route them in a way that'll cause a short. I then took a long piece of solid core wire and connected the backside of all the diodes together. This long piece of wire will ultimately connect up to the write signal. which is only available on the adjacent board. That's why I pulled these two off together as a single piece. I'll have to be careful of this in the future if I ever want to remove this board again. All right, here we go. Let's give it a test. We'll run it. It should clear out anything that's down here. Yep. Let's go ahead and put in our first value. We'll just do 5, I guess. We should see 101 show up on the output register. That's definitely an improvement. And let's add 1 to it. So I'll flip the far bit and just the first bit. We should see that become 6. Yes, all right. We just did 5 plus 1 equals 6. Okay, let's turn all those switches off. We'll run it. Cleared everything out. Let's load in 5 again. There we go. And let's subtract 2 from it. This should give us 3. Yeah, there we go. We just did 5 plus 1 equals 6. And 5 minus 2 equals 3. We have created the worst calculator in the world. And I just finished putting this thing through its paces. I ran probably another 20 calculations through it. It did every single addition, every single subtraction, 100% perfectly without missing a beat. That's it, y'all. The UE1 works at 100%. We have tested every single function of the CPU. We've tested every single spot in memory. The paper tape reader hasn't missed a beat. It's complete, y'all. And that brings us to the end of the UE1 series. This is the final episode, the last episode that we will ever have on this machine. It's the end of an era. This is a little crazy. When I started this 3 years ago, I had no clue what I was doing. I just kind of dove in and started building stuff, and I never thought I'd get to the point where it's reliably running code. This is a fully functional homebrew computer, my first homebrew computer ever. And it is now finished. Which means it's time for more homebrew computers. We have the UE2 coming, which is gonna be vacuum tube based. I'm taking a lot of the things that I learned on this one. We're gonna dive into different types of memory. We're gonna really try and push the limit of our ability using everything we learned with UE1. But before we get into UE2, there's a little bit of silicon that I want to dive into first. I want to build a homebrew computer based around the TMS 9900. And now that the UE1 is finished, it's time to dive into that. So that is the very next homebrew project that is coming up. I'm very excited about it. And who knows, maybe it'll teach us a little something extra that we can then apply to UE2 to make it even more awesome. So I want to thank you all so much for watching, and I hope to see you in the next one.